So this is the last presentation of this course.
Don't forget us.
We hope everyone has had fun. We're gonna start. So we're the last team. We're the semiconductor team. So who knows what's a semiconductor? Can someone please raise your hand if you do know? Okay, who knows what's a semiconductor made of? Okay, good. So I'm gonna give a refresher to everyone from your high school chemistry class. So a semiconductor has basically three elements. The first of one is sort of like a glass. So the glass is an isolator, meaning electricity won't pass through it. And then you have metals, which will allow electricity to flow through it. When you mix both of those elements, you get something called the silicon. And inside the silicon, you have the transistors. Think of a transistor like a switch, so you can turn it on and off, letting energy or electricity go through it. So semiconductor is mainly a material made of silicon. And this property, semiconductors, are basically the brains of nearly all modern electric devices. So why are they critical? They're more than a power source. They handle data, connectivity, essentially everything from phones to medical devices. Everything you use has a semiconductor. And so even though semiconductors have been present for a long time, since 2019 up to this day, AI basically changed the game. To give you an example, NVIDIA, one of the biggest players, used to be mainly known for video games, and then there's semiconductors, which are used for training LLMs, just changed this market hugely, no? And then fourth, why is it important for the global economy? So they support strategic sectors such as defense, so your tanks, your fighter jets, the supply chains, infrastructures, telecommunications, everything that is of vital importance to a country has advanced semiconductors in it. And that's part of the reason why the United States is imposing pressure on these companies for strict regulations and sanctions that prevent export of advanced semiconductors to rival nations like China. So to give you an idea of how big this market is, up to this day is almost $500 billion. By 2033, it's going to be worth a little more than $1 trillion. This is conservative estimates. It's growing almost 8% compounded yearly. So NVIDIA, which is worth a little more than $3 trillion, if countries would be, their GDP would be their market cap, their valuation, NVIDIA would be the third largest country in the world. So that's how big this market is. The memory segment represents 23% of it, which is usually for cloud computing and virtual reality. And then almost 30% of it is for smartphones and connected devices. Now, how is the market share? So half of this is mainly controlled by Asian Pacific countries, and mainly China, Taiwan, and South Korea. So that's why the US doesn't want to import China to invade Taiwan, because they would just have all of the manufacturing power for the semiconductors. Then North America has 22% of it, especially for telecom and automotive technologies. And the CHIPS Act has been one of those big bills that's just putting a lot of effort to make this market share bigger for the US. And lastly, Europe, mainly France and Germany, hold the market share in the automobile applications. I'm going to hand it over to Anesh so he can show you the key players. Like this one.
Yeah, I think it's pretty widely agreed that semiconductors are probably the most advanced mass-produced technology out there. So you've probably heard of the NVIDIAs of the world, but I'll kind of break down some of the more lesser known companies. Maybe you haven't heard of Broadcom, which makes ASICs and like networking things, and ASML, who do a lot of the design tool stuff. So we kind of split it up into 4 different categories. So chip design, manufacturing, including packaging, which is a newer segment, design tools, and fabrication tools. So as far as chip design goes, these are the companies you most probably know most about, simply because most of this is in America. It focuses on designing and optimizing integrated circuits. And depending on the situation you need the semiconductor in or the applications you want to use it for, you make different trade-offs in terms of performance, power, and area used for certain types of transistors and things like that. So you need to worry about logic design, the physical layout, and verification as well. So chip manufacturing and packaging, this is a volume business. So basically, if these fabs, these are what the factories for chip manufacturing are called. If they're not full, they're losing money basically. And this is basically the process of etching these transistors into silicon wafers. And they do this using EUV technology now. I'll explain a little bit more of what that is when I talk about design or manufacturing tools. But we also see things like packaging being a bigger thing now with advances like advanced packaging, which allows us to combine chiplets or even stack chips as well. And then we also see just continuous improvement as we try to get smaller and smaller in this space. And the biggest thing you want to look out for in this world of chip manufacturing is yield, as that is a key concern of just constantly improving your yield for your processes, especially as you go down into lower and lower nanometers, as it is harder to make effective designs that way. So next, we can cover chip design tools. So some companies here, Synopsys and Cadence, these are pretty big in the space. And it currently takes around like 2 to 3 years to design a chip, which can be used for mass production afterwards. And this has been done through these company software. And it allows you to design, simulate, and verify your chip architectures. It still takes 2 to 3 years just because how complicated these RTL designing is, physical layout, and timing related stuff. Interestingly, Synopsys just recently acquired another company called Ansys, and that's been a big thing going on in that space. And then we have chip manufacturing tools. So you might have not heard of any of these companies actually, but they're pretty important. ASML is a Dutch company, and they basically make these EUV machines. Each one of these machines costs around $300 million. And if you look at a fab in total, those cost about $20 billion itself. So when you look at the CHIPS Act and they're giving around like 10 billion, 5 billion to different companies, it is still just not enough to cover a whole fab. And these companies have to put in their own money. But basically, they do things such as lithography, inspection, and making sure the yield is good and you're able to make transistors at a very small scale and level. And then you see other companies here like KLA and Tokyo Electron that do things with photoresist and defect detection.
Thank you, Anish. All right, so let's talk about something cool, the fab. So now let's talk about something cool, which is called the fabless model. You guys all know the biggest fabless model is NVIDIA. They designed the really brilliant chips, but they don't even make them. Instead, they outsource the manufacturing to the giants like TSMC. But why they do this? Well, it's actually a very smart decision because they can focus more on innovation while TSMC handles the insanely complex manufacturing process. And as is shown in the right, fabless companies like NVIDIA specialize in chip design, And the foundries like TSMC focus purely on the manufacturing. And in the middle, you can see the Intel and Samsung. This is called the integrated device manufacturers. They do both under one roof, making each type of company play a very unique role in the whole semiconductor industry. And here's the thing, the model is everywhere now. It's become a huge trend in the semiconductor world. So why is fabless taking over? Let's dig in and find out. Well, we think the fabless model lowers costs, improves quality, and lets NVIDIA focus more on its innovations. And it is how NVIDIA captures the AI GPU market without the huge financial weight of running the $1 billion of the fabrication plants. So let's also take a moment to appreciate the heroes of modern technology, these advanced manufacturing techniques, which is really amazing. We can see that progress in 5 and 3 nanometers transistor scaling enables smaller, really more efficient chips. And the chiplets with the 3D stacking improve the performance and energy efficiency. Also, the EUV lithography and material engineering tackle the challenges of high-density chip production. But what makes support these amazing techniques? Let's talk more about the power efficiency. It's important to first get to know about the process of the chip manufacturing. Chips go through a wild journey from sand to silicon, wafers, and finally become the high-performance processors. But here's the catch. AI chips and data centers consume tons of energy and generate massive amounts of heat, which requires advanced cooling systems like liquid cooling and water cooling. This even leads to more water waste and carbon emissions, which may make the pollution on the earth. So to tackle this kind of problems and to make the sustainability, companies like Samsung and Intel are turning to the greener and more sustainable practices. Like the goal is to support the chip growth while shrinking their environmental footprint.
Next, I'm going to talk about the growth opportunities in this area. Since we talked about all the challenges, what are the growth? What are we looking out for? We're going to spend the next couple of minutes talking about the growth opportunities from these 4 areas: the market expansion, the governmental incentives, the vertical integration, and the new technologies and materials. In terms of market expansion, as we talked about quantum computing yesterday, there's huge opportunities trying to expand this market to many different areas, including looking into more advanced technologies. Sorry, give me a sec. Advanced technologies in quantum computing, as well as automotive vehicles, RFID tags, as well as healthcare, like healthcare imaging, and wearable devices like your iWatches. In terms of governmental incentives, we know there are US chip tax, the EU semiconductor initiatives, and all the other governmental incentives help the semiconductor manufacturers to grow in different countries as well, especially in the US. In terms of vertical integration, we expect to see some of the bigger companies acquire fabrication abilities, as well as some of the companies at Intel and Samsung Semiconductors to acquire more fabrication abilities to streamline their operations. We also expect to see some new technologies and materials emerging, like our guest speakers will cover in the future, later on, about the developments in new technologies, as well as using some new materials to build faster and more efficient chips. Next, we're going to talk about challenges in this area.
So we identified the 4 main challenges facing the semiconductor industry right now. The first one is geopolitical tensions, and then the high cost in manufacturing, the talent shortage, and also environmental and regulatory pressures. So let's dive deep into the first challenge. which is the geopolitical tensions. So we found this kind of funny meme trending on X to kind of entertaining people on the critical situation and why Taiwan's become a hotspot right now when we're talking about the whole supply chain of semiconductors. So the fact is that Taiwan's kind of dominating the manufacturing of semiconductor industry thanks to TSMC, and they produce over 90% of the world's most advanced chips. And this makes Taiwan very critical and also a geopolitical flashpoint. And its location makes Taiwan very vulnerable to any potential military conflict or just natural disaster. Anything happen to Taiwan can potentially disrupt the whole global semiconductor supply chain and causing massive economics and also technological setback. So countries has, of course, reacting to this supply chain vulnerability by, investing billions of dollars, try to build their local chips factories. But then it's very difficult and challenging to replicate Taiwan's semiconductor expertise and also the scale that they have in a short term. And it's not just about the story of you building up a factories, but also it is a story of how you can recreate the whole entire ecosystem of knowledge and the skills that Taiwan has been accumulated over the years. And if you guys want to get a more comprehensive view of, the tensions between the countries and also the story behind, we highly recommend you to read the book Chip War by Chris Mueller to understand more. And another thing why it's very challenging and also it's going to be a long-term plan to replicate Taiwan's capability and also the skills is the fact that building these semiconductor factories is a very capital-intense type of business. And this is a estimations of the cost to build this fab, which has been significantly increased over the years. And by now, in order to set up a semiconductor fab, it will cost you more than $25 billion US. And all the costs as accounted for, the needs for cutting edge tools and also the complexities of the designs of the chips and also packagings, which has been mentioned earlier by Anish. Another challenge is the shortage of talents. And there's a report done by the Semiconductor Industry Associations, which estimated that within the US only, by 2030, there was around 58% of new jobs across manufacturing and also designs with risks going unfilled. So there's a huge gap between the demand for skilled workers in the industries and also the available talent pool. And there's a loss of, empty roles for engineers of all levels and also computer scientists, which the semiconductor industries has also have been competing with other industries, especially with software and AI. And the last challenge is the environmental concern. We mentioned this earlier in our presentations, but just to give you guys an example, an average chip manufacturing facility today, they can consume 10 million gallons of ultra pure water per day, which this is the type of waters which is thousands of times cleaner than our drinking waters and will be used to remove impurities, which can damage the chips during their manufacturing process. And this kind of water uses is equivalent to 33,000 of US household daily uses. So just one example to show you guys how much the higher amount of water consumptions that would be required by these factories. And now passing over to Sarah to share a unique case study in this industry.
Thank you, Lynn. So far we've heard the name NVIDIA multiple times, and we mentioned that chips are the new spice. So how are we focusing on the monopoly of chips is by studying NVIDIA. So fun fact about NVIDIA, it has not been doing well all along. So it started off and was founded in 1993, which is 31 years ago. But their first commercial chip was successful in 1997, but it did not make enough revenue because of their, they didn't have enough demand at that point. But they also made really strategic decisions in making sure that they become a key player within the market, by investing heavily in and forecasting the importance of AI. So in 2006, they opened up an open source CUDA, which was released to help GPUs with software and developers to have access to also improve on the code. So as you can see, we need to understand the difference between CPUs and GPUs and why GPUs succeeded in that realm. So CPU, think of it as a sequential processing task. So you have to finish A before you go to B. And then you have GPU. Think of a pixel. When an image is being laid down, every pixel needs to be illuminated parallel. So in the realm of AI and artificial intelligence and machine learning, the need for massive matrix multiplication and data analysis and graphic units increased. So the more you go into specialized chips like GPU, FPGA, and ASIC, which is specifically integrated chip, the higher the efficiency, but it is less flexible. So NVIDIA was targeting a specific market for a really long time until they pivoted into the data center market. So their strategic moves had helped them in the past couple of years to be the main resource for GPUs, even though they outsource their fabrication. As mentioned, their early strategy is opening up CUDA, so researchers and developers would help improve their open source. And the second one is making sure that they integrated themselves heavily in the data center realm because they saw the need for higher processing and lower latency in that space. And then they also had a really good strategic partnerships designed to help them like branch out into the economy, which they work with Google, they work with Amazon and multiple other companies. But what is the future? Is NVIDIA the one and only name are we gonna hear? If you remember on Monday, I said that thermodynamic computing should be the new future and we need better hardware to process in a more sustainable way. So we believe that new startups and new disruptive developments are gonna take over because of their futuristic look on how to make computing more efficient and more sustainable. So what we would love to introduce is Blumind. It's a Canadian tech-based company that produces chips for faster processing. And our guest speaker is going to tell us more because he's the co-founder and the mind behind this operation. He's also a Cornell MBA graduate, so help me give him a warm welcome. After Niraj.
Thanks. Yeah, if you can switch over to mine.
Oh yeah, I can. Did you have a USB?
I think this will work. Let's try this. All right. Thanks, and great introduction, by the way. Doesn't leave me a lot to say. Very, very comprehensive. Thank you so much for having me here. My name is Niraj Mathur. I'm one of the co-founders at Blumind. Blumind is a startup in the semiconductor space on a mission to develop the world's most energy efficient processors. Okay, and you heard a little bit about why this is important. I'm going to give you a little bit more color on that. First, a little bit about my industry. I've been in the industry for over 20 years now and worked in many different roles. I started off on the hands-on engineering side, moved from there to engineering leadership, management, moved to marketing, product marketing, strategic marketing, business development, and then had the hunkering to do my own startup a few years ago. And that's what brought me to Blumind. But let me talk a little bit about the industry at large. The semiconductor industry can now be considered to be a mature industry. Okay, it's been around for a while. I would say from around the 60s is where, you know, the modern transistors came to be, and a really smart individual, Gordon Moore, from Intel back then in the mid 60s, kind of made a prediction, which was uncanny in how accurate it was. He made a prediction that the number of transistors on these devices are going to double approximately every 2 years. Okay. And he just threw that out there. And if you map, you know, there's a chart here off to the top left. If you map how his prediction has played out over the last 50 odd years, it's been pretty bang on. Okay. He's been quite accurate in that prediction. And so the semiconductor industry, fueled by a ton of really smart minds, has been, even though it's on the bleeding edge of technology, has made technology quite predictable and has kind of followed this curve of every year after year, coming out with something that is so much better than what was there last year. All of us buy our iPhones and we expect the performance to be vastly superior from the one you bought last year, right? And that's thanks in large part to this industry. So we've been benefiting from this very predictable nature of semiconductor development, where there's R&D innovation happening that drives lower cost, adds more function and features. More applications come online from those new features, new capabilities. That drives more revenue. That fuels more R&D innovation. And this loop has been happily going on for 50 years, right? Great. However, today things are not as hunky-dory. Okay, things are changing. There's a massive shift happening. For one, Mr. Moore, who made this awesome prediction, his prediction is now no longer holding true, because we're kind of getting down to molecular limits of how small you can make these devices. These things are already, the features on a chip are already 1,000th the size of a human hair, right? So they're minuscule. And now you're getting into actual molecules of these elements that build these chips, that you can't maneuver them, you can't manipulate them any further. So the cost of production is skyrocketing. Okay, so in fact, for the last 10 years or so, the cost of building, this is a metric, 100 million gates. Think of it as the size of a chip or capability of a chip, has basically plateaued, right? About 10 years ago. So as we push into lower and lower geometries, as we continue shrinking things, they're not getting cheaper anymore. Okay, so that's number one. And number two, the performance is kind of plateauing as well. So you look at this curve where CPU performance, what we were used to seeing 2x, 1.5x, 3x, 3.5x over, you know, year-over-year improvements, or maybe even every 2 years. Now we've got to kind of the end of the line where performance for a single CPU core has flatlined. Okay, now we're at hitting 2x over the next 20 years. Okay, that's a bit terrifying, right? So people have started working around this by putting a lot of cores on a single CPU and parallelizing processing, but the core processing unit has kind of flatlined. So this is troubling because it kind of threatens, it jeopardizes this amazing progress we've made over the last many decades. Another huge dynamic, which was touched on by the students that came on earlier, is it's just the energy density, the energy needed to drive all this compute is skyrocketing, especially with the advent of neural networks and this machine learning approach to solving problems. This is something that AMD put out there a couple of years ago, that if this AI workloads continue to grow at their current rate, within the next 30 odd years, the energy needed to do this processing is going to be over 90% of the energy produced by humanity today. Okay, so this is a serious challenge facing us, and quite frankly, we don't have a good answer for this yet. Okay, this is what's a topic of discussion today. And meanwhile, we have AI, right? AI is now pretty much everyone can agree that it is massively changing our world, right? Whether it's in consumer wearable devices, in our smart homes, smart cities, in our cars, or in our data center and cloud computing, devices are getting all the more smarter, right? One thing you have to keep in mind is everything, all of this AI, all software runs on chips. And these chips, because of the challenges of older architectures that have been used all these decades, are operating very inefficiently for neural networks. And this really threatens the future prosperity and these future use cases and applications that are projected to come online, right? But we want to have robotics, we want to have human augmentation. I wanted a nice little robot to do my dishes and cook for me every day, right? We all want these things. Well, all of these things are going to be fueled by the next generation of semiconductors. And right now, that is all in jeopardy because we don't know how to grow, right? Here are some future trends that are developing in the industry to meet some of those needs. One on the left-hand side is folks are moving away, and this was touched on in the presentation as well, moving away from general purpose CPUs and GPUs to more domain-specific processors. So if you're running a neural network to run a LLM, you use a particular type of processor that gives you the best performance for that workload. If you're doing, running a DSP algorithm, you use a processor that optimizes that workload. So really optimize the architecture of the processor to the workload that you're trying to solve. So that's a trend that's playing out right now. Blumind, my startup, is one of those domain-specific architectures. I'll touch on that a bit more. And on the right-hand side, there's this concept of how do you package these silicon bits together? There's all kinds of work happening in this space that's basically saying, okay, there's better ways of integrating functionality rather than a monolithic silicon die. You can have multiple chiplets of silicon that can be connected together to deliver a function, and you can stack these in a 2.5D way using an interposer or in a 3D way. So there's a lot of innovation happening here that again is attempting to continue to deliver greater functionality at lower cost, kind of like what Moore's Law was doing these last few decades. I will touch on this one next. So now, I'm a startup. I'm not NVIDIA. Okay, you heard a lot about NVIDIA. Doing a startup in the semiconductor space, and I'm going to touch on this a bit because I hope a lot of you are going to go off and found companies of your own. Doing a startup in the semiconductor space or any deep tech space is slightly different challenge than your typical SaaS startup. It is much more capital intensive. It's a longer time to revenue. Right, it takes a good 3 to 5 years to develop your product, find product market fit, all of those things, right? So as a result, this is the typical sort of timeline you can expect, starting from a pre-seed seed to Series A round. You can expect to raise between $10 to $20 million to get that far, and here you basically have your first product prototypes come out, and that's about a good 4 or 5 year journey just to get that far. And then after that, you really have your growth rounds, your Series B, C, and so on, and finally, hopefully, an exit a decade down the road. This is a very typical trajectory. You saw the trajectory NVIDIA was on. I mean, NVIDIA almost went bankrupt many times along that way, and it took Jensen good 25 years to really figure out the path. And some would say they kind of stumbled into AI. They were really a gaming company, right? They were doing graphics processors for hobbyists and gamers. So it's a complex space, but really rewarding. And if you execute properly, it's a great journey. The other dynamic that's going on in the industry is this, I think this was touched on as well. In the past, you had companies like IBM and Intel that were IDMs. They were fully integrated, vertically integrated. So IBM would sell servers, would develop the chips, would design them, would manufacture them, would package them, all of that, right? And consumers would buy the final server product. Now, that old model has basically been wiped out. Now with the advent of these fabless semiconductor companies over the last 25 odd years, you have a much more disaggregated approach where, because there's so much expertise and depth needed for each of these little domains, it's impossible for one company to really excel in all of it, right? So there's this kind of disaggregation happening, and you've got now companies specializing on the system development, memory, packaging and assembly, equipment manufacturers, foundries, they're all different. Blumind, my company, is a fabless semiconductor company. So we do the design and we outsource all the manufacturing. We don't do any of the manufacturing in-house. So this is a new dynamic that has happened as well. Now, I'll touch a little bit more about this domain-specific architecture and in particular what Blumind is doing. To the left side of this wall is your traditional approach to compute, which is to have memory elements, compute elements, an instruction set that gets compiled from software and runs on these and utilizes these resources to solve a problem. This has been the approach. It's called the von Neumann architecture, which is like over 80 years old, okay? But all modern day computers still follow some variant of this architecture. The challenge with this is it served us well for human written sequential code, but it falls apart when you have a massively parallel compute intensive workload like machine learning processing and the matrix multiplications that were brought up on the previous chart. So our industry has done incremental improvements to this architecture over the last many decades, moving from CPUs to GPUs to near memory compute to at memory compute to in-memory compute. But all they've managed to do is reach about 40 TOPS per watt. TOPS per watt is a measure of compute efficiency, tera operations per second per watt, okay? And today, the bleeding edge in the world is about 40 tera operations per second per watt. And it's not NVIDIA. NVIDIA is about 8 or 6 TOPS per watt, something like that. The startups in the space doing this von Neumann digital approach are around there. Blumind is on the right side of this wall. Our goal is 1,000 TOPS per watt, okay, and beyond. That's kind of where we're starting. So you can see it's a couple of orders of magnitude in terms of performance efficiency that we're going for, and we think this is really what's needed to drive the proliferation of AI for everyone everywhere, right? In every device, in every scenario. Once it is this efficient and this cheap, we can accomplish that. So that's what we're trying to enable. The way in which we're doing this is we've gone back to first principles. So that von Neumann architecture was really written for human written software, right? Neural networks are not that. Neural networks are much more like what we do in our brains. Our brains are not computers, right? Our brains don't have a software and instruction set and memory here and compute there, right? That's not how our brains work. Our brains are biochemical neural processors, right? We take sensory information from our sensors, our sight, our sense of hearing, our sense of taste. These are all analog parameters that get fed into our brain, which learns over time, right? A human child, you can show him or her 2 pictures of a dog and then show them a real dog and they'll be able to tell you that's a dog, right? Machine learning can't do that, right? Neural networks cannot even do that yet. You have to throw much more data at them. So machine learning is a completely different type of workload. So we've gone back and said, okay, how can we design a computer that more accurately represents how our brains work. And we went back and developed an architecture. This was my co-founder, actually, John, who's a physicist and an IC designer and a data scientist rolled into one. And that's what it took to come up with something like this. And he basically outlined an architecture where we use single CMOS transistors as synapses of our brains to store neural network weights and perform the matrix multiplication all in that one transistor device. So we're leveraging the device physics of this transistor to do that. We have capacitors to sum outputs of those multiple synapses and store the result. And we have temporary memory to store store activations between neural network layers. So this is a lot of technical, I'm getting a little bit technical here, but suffice it to say, this is what drives the efficiency. Okay, we're moving away from that event-driven clock digital architecture, which was for human written code, to a much more natural, thermodynamically efficient and appropriate architecture for neural networks. Okay, in addition to this, because we're doing things in an analog way, we can interface with our analog environment, okay? Everything we hear, we see, we touch, we measure, these are all analog parameters. In today's world with digital processors, the first thing we do when we measure these analog parameters is we digitize them, okay, with a digitizer. That's kind of the first thing we do, and then we ship it over to a digital processor. What we're able to do with our analog computer is take analog information from these sensors and send that analog information straight into our neural network. This, again, is much more similar to how our bodies and brains work. And it has the advantage of eliminating that digitization step, which consumes power, consumes energy, and it also adds to cost of the system. So this is another optimization that comes from doing things this way. And this approach really enables more on-device smarts with much lower energy consumption and much better performance as well. So in all of these workloads, these are just various neural network models. We've got recurrent neural network for keyword spotting, like your Hey Siri, Hey Google kind of wake words. You've got in cameras, detecting, for example, a human is in front of your camera. Imagine a battery operated camera that needs to store information when it detects a human in front of it. So a VGG11 network for that. Always on gesture. So for example, for your AR, VR headset, when you stick your hand up in front of it, it recognizes a swipe or a click or something like that. And then again, an object detection classification in a video stream here, MobileNet V2. These are standard neural networks. And you can see our solution is always about 100x or more efficient than any of the competitive, the basically the industry standard digital solutions today. And this is what our customers are really interested in doing. Now, we're not a technology company. We're really a commercial venture, and my co-founders and me, we're passionate about getting our products out in people's hands, and hopefully you will be able to buy products with Blumind silicon in it fairly soon. We've done a number of silicon tape outs. So we spent about 3 years in R&D mode, where we're developing our foundational technology, getting our patents granted. After that was completed, we did, and that included a couple of test chips that we built as well to test out in the lab our silicon. That's our lab up in Toronto. And we've engaged with customers. So pretty much from day one, we were pitching our ideas to customers that this would resonate with. And the first market we found was really consumer wearables. You can imagine, your smartwatch, mine, this product I have to charge every night or it's useless the next day, right? So there's a real need for these devices as they add more intelligence to extend their battery life. So we found great use cases in the wearable space. There's new categories of products coming up like smart glasses that suffer immensely from lack of battery life. So we're finding a lot of traction there, but we're also finding homes in automotive, and smart homes, in various other markets, medical and so forth. So this is the journey we're on. I will end with one kind of summary chart that I actually had earlier on here, and then I'd love to get your comments. So yeah, some key takeaways, right? Semiconductors are resurgent. We have been in this mature industry mode, and we've been kind of forgotten as, the focus was on software because, hey, the chip's just going to get better, right? Year after year. That was just the assumption, and it held true for such a long time that nobody was really paying attention to what was going on in this space. But now, because of the reasons we talked about, this is no longer true. AI is profoundly hardware limited today, and these problems, these challenges have to be addressed with new innovation, new ideas in the silicon space today. Semiconductor startups, we have huge challenges. We talked about some of the challenges about capital, time to revenue, and so on. But there has actually been a sustained decline of venture capital investment in semiconductors over, if you look at the last 25, 30 years. There's a little blip now because of AI and people realizing that, hey, this actually, we need to start investing in the space again. But we have been underfunded for a long time. The focus has been mainly on SaaS startups. So this is something that I'm looking forward to change. There's a number of investments. You guys talked about the CHIPS Act. So governments are stepping in because this kind of red light started going off a few years ago when people couldn't buy cars with their, people were buying cars with features missing because they didn't have chips to assemble these cars. So the government stepped in, and there's a lot of public money now floating around. There's about $800 billion worldwide that got invested from the years 2020 to 2023, thereabouts. So there's a lot of investment, and people are playing catch up. And that old order, that supply chain that was built over the last 30 years, highly optimized with concentration in Taiwan, right? That is now being dismantled because people are realizing that efficiency and low cost are not the only considerations. There's a lot more things like national security and robustness of your supply chain that come into play here as well. And we really need to build up the startup playbook. So we need to have funding streams that are geared more to semiconductor startups. That's still, I think governments are now relearning what it takes to do this kind of work and how to support startups here. And I think that the successful companies like NVIDIA and ARM and AMD, they're actually playing a very key role as well. They're coming in and they have huge startup supports, and they have corporate venture arms that actually support many startups in our industry. And I'm hopeful that all of this is going to lead to great outcomes. If there's one thing that comes out of me talking to you today, I hope some of you will pursue a career in this industry. Believe it or not, I'm considered one of the young guys in the semiconductor industry, and I'm not. There's a huge gap of talent. Okay, this was touched on earlier as well. It is real. There's a massive gap of talent. Kids that saw semiconductors as a boring, mundane, kind of turn the crank industry, and saw innovation as really being in the software space, need to take another look at this, because this is where things are getting really exciting. There's going to be tremendous opportunities over the span of your careers, that I think you guys should all take a serious look at. Okay. Thank you.
So we can open up the floor for some questions, or we can ask more questions and you guys dive in.
They're immediate questions, right?
Yeah.
Yeah, go ahead.
So,
Bring more chairs.
Yeah, some chairs. Yeah, go ahead.
Thank you very much for the amazing talk. It's really fantastic. And I really believe that this is the future of the semiconductor, actually. We human beings just use our brain with less than 20 watts to do the object detection, etc. And why the computer cannot do so. Yeah, I totally agree with that. I'm wondering if you could tell me, tell us something about what's the most difficulties while realizing the process, and if there is any current result also.
When you're saying difficulties, when you're saying difficulties in the process,
Yeah.
what process are you referring to?
Crafting this problem.
Oh, just developing the solution?
Yeah.
You know, I would say the biggest difficulty is inertia, right? Even a big company like NVIDIA is set in their ways. Okay, they've built a ginormous business around the GPU, and they have, you know, they're ruling the world right now. Getting them to really look at, hey, there's a better way of doing it, guys. You really need to look at neuromorphic compute and this brain-inspired approach. It's difficult to do, right? So I think the bigger companies will really struggle with that. Also, another thing I'll say is, as I pointed out earlier, some of these innovations are multidisciplinary innovations. Okay, so for example, for John to come up with that architecture that we're commercializing, he's a unique individual with a physics background and IC design background and a machine learning background and deep knowledge in all these three domains. That's really what's needed for this solution to come out. And it's really hard to have those disciplines come together. So those are some of the challenges, and I hope my colleagues and some of these companies with more resources look at some of these things more seriously. So that's what I would say. All right.
Well, thank you very much.
Yeah, thank you.
Thank you so much, Niraj, for the
Yeah.
talk. So my question is more towards like NVIDIA, which is preparing for a post-GPU AI inferencing, including application-specific integrated circuits. So how is Bluemind's analog compute being positioned and customized for ASIC-based inferencing era?
Okay, so what we're developing is a foundational technology, okay, using this, neuromorphic approach for solving neural networks. It can be used in anything, really. It can be used in ASICs that are built for a particular neural network. So we're looking to scale this. Right now, we're doing smaller size networks, but we can scale this up to doing, LLM class networks as well in the future. So I would say it is broadly applicable to all of these products. Okay, we just have to prove that it works in at least our first commercial product, which is what we're trying to do this year. And then it will have broad applications. And maybe I'll knock on Jensen's door and ask him to buy it as well.
Thank you so much.
Yeah.
Thank you so much for the talk.
Yeah.
So my question is that earlier we used to have this hard disk drive.
Right.
Afterwards comes this solid state drive with HP and Mac probably using it. And they worked on the flash memory, so that's why they were a lot faster.
Yeah.
And nowadays, the cloud is there. So from a design perspective, how do you see, can we have a situation where, these electronic devices, be it PC or laptops, working entirely on cloud-based memories, which is essentially doesn't use semiconductor and not on any sort of semiconductor-based.
Well, I mean, keep in mind, cloud, it's not really in the cloud out there, right? There are semiconductors, there's servers physically somewhere that are actually running your workload, right? So all of this is still running on semiconductors. I personally think that, yes, while recently there has been a big push to move things into the cloud, and it'll continue to be the case. I mean, this market is going to continue increasing. a vast number of use cases that will require intelligence on the device at the edge for a whole number of reasons. If you were driving an autonomous vehicle, for example, and that processing to detect a pedestrian, to dodge, avoid hitting, if that processing was happening in the cloud somewhere, would you be comfortable with that, right? Would you have, 5 nines reliability to say, yeah, you can respond in less than 10 milliseconds to a pedestrian in front of your car? I don't think so, right? I would want that on the car and not rely on any kind of link to any cloud, right? I want highly reliable deterministic service. Another area is, well, if I have a pair of smart glasses that I'm using to navigate my world, going shopping, asking for information on things I'm looking at, for example, do I really want all that information going into the cloud and being run there? Well, maybe not. I have privacy issues, right? I have privacy concerns. I don't want that information being open to other people. So there's a lot of these considerations that come into play. I think there will be a large number of use cases that will need more intelligence at the edge. One of the big markets that we're most excited about is robotics, okay? Natural movement processing places all kinds of challenges on having intelligence on the device. So this is where we think that this paradigm will really need to come to play.
Thank you.
Yeah.
Hi, thank you for the great talk. You mentioned that Blumind has been underfunded through times, and I was just wondering, what's the turning point and what was the key to finally convince the VCs to invest?
That's a good question. I don't have a straight answer. I'm trying to raise a round of funding right now, actually, and I just had investor meetings in Manhattan this morning. I don't have a great answer to that. All I can say is, and this is something I've learned through this process. We've raised a good chunk of VC money, and what I've learned is there's no one thing. The main thing is make sure you're aligned with the VC. They value the market you're trying to target, the technology that you bring to the table, and get to know the partners, the people, the decision makers in that firm, because they're the guys that are actually going to support you and work with you. So even though you tend as a founder, like when I went out and raised my first round, I was like, well, it's a faceless VC, right? It's just a firm. I have to make a pitch, send a deck in, and boom, they're going to say yes or no, send me a check in the mail, right? That's not how it works. Most of at least in my experience, the times I've been most successful is when I've built a relationship over the course of 6 months to a year with a investor that really resonates with our space, our mission. That's when they come around and make an investment. So that's probably the best advice I can give at this point. Yeah.
Thank you so much.
Yeah, I got a question. So,
Yeah.
sorry.
Yeah.
Thank you for the talk, by the way. That was great. So we kind of touched upon this earlier, but there's these established companies in the space, and I know like Intel, Qualcomm, Mac, they all have these NPUs coming out, as well as I know IBM and Intel have their own versions of neuromorphic computing, like North Pole or something, and
Right.
Lowy. So how do you differentiate yourself as a startup in an industry that's like very monopolistic, very capital intensive?
Yeah, it's like anything, right? I think startups are where stuff can happen at, maybe 5x the pace and 10% of the cost, right? That kind of value, it's really hard to do that in a company like IBM or Intel or any of the ones you named, right? And the big guys know this as well. They know this. So we get a lot of interest, and some of our lead customers are these big guys, right? Because they know they cannot drive that pace of innovation that's needed, that we can drive, right? Where they excel is when a idea is proven and you need to now scale it up and drive many use cases, engage with many customers and support those customers, that's where their machine really comes into play. And that's where we will end up partnering with many of these folks.
Actually, I have a question.
Yeah, sure.
Personally, I'm very interested in the marketing field. So, in terms of the marketing and sales strategy, is there any significant difference between the semiconductor giants and the startup like Blumind?
I mean, yes, there will be differences. In a startup, you can expect to have a much broader breadth of responsibilities and exposure. So you may be doing, driving the channels. You may be driving PR and outbound marketing. You may be helping with product definition and giving feedback to the engineering team. You may be doing some business development type of activities. You may be doing events and trade shows. Whereas in a big company, those would probably be separate individuals working in each one of those domains. So in a startup, you can expect to get a lot more breadth. So if you have that interest of really getting broad exposure, then a startup is probably a good bet.
Well, thanks for sharing.
Yeah.
Hi, how's it going? I have a question.
Yeah, sure.
Thank you for the talk. I was wondering, you talked about smart glasses and the use case of rendering on device. Like in this new method that you've developed, the analog processing, is graphics comes into play as well? Because like it's processing the smart AI, but in terms of like generating graphics in 3D, is it also something you are mastering?
No, so we don't do any generation of images. We are solely focused on processing and running inferencing operations for neural networks. That's what we're solely focused on. Everything else in the device, like rendering the graphics and the sensors as well, right? We don't develop the sensors. We're really maniacally focused on the compute aspects of machine learning. And as a startup, we absolutely have to be. If we bite off more than we can chew, we're going to fail. So we're really focused on just this aspect.
Thank you.
Thanks.
So we're out of time, but thank you all for your questions. I would like to close out by actually reiterating your bio because it's impressive, and then we can ask you one last question.
Oh, sure.
About
And I'll stick around for a little bit longer. So if you guys want to come chat, I'll be here.
So for over 20 years, Niraj has been a leader in the silicon and hardware arena with a broad industry experience in strategy, marketing, business development, product engineering. He has held senior leadership roles and led global cross-functional teams to support these disciplines. He's passionate about building scalable startups with extraordinary technology and vision. He's currently a co-founder at Blumind, a deep tech semiconductor startup, on a mission to build the world's most efficient neural network processors. He holds an MBA from Cornell University. So to reiterate, thank you so much. We had a pleasure speaking with you. And our question is, because you've had multiple startups experiences, how do you pinpoint potential opportunities in that space and you hedge your bets in that realm?
Yeah, it's a good question. I like to start from the market. I like to start from how big is the market potential for the technology, right? I like to have a very big TAM to start with. If your TAM is tiny, then everything gets tinier from that point on. So that's one big thing I look for. And in this case, that resonated immediately because I was like, okay, machine learning inferencing, that's going to be everywhere. That's a big TAM. The second thing is basically the differentiation of your technology, right? So how defendable is the value, or how defensible that is, right? You have to look at other research happening in the world. I mean, there's incredibly smart people working in the space continuously, right? And we get almost a startup every week or a couple of weeks that pops up on our radar as, oh, they're doing something in this space. So for a space like this, it's really important to understand how defensible your IP is. And yeah, those are the main two things that I look for. There's a whole bunch of other things below that, including your co-founding team, which I think is absolutely critical as well. But those are some of the top two things.
Thank you so much. Please give me, help me give Niraj a warm welcome. And this is of our appreciation. Thank you again. And good luck with your investors.
Yeah, no, thank you.